Welcome back. In this section, we'll be looking at the sum and difference formulas for sine, cosine, and tangent. And these formulas allow us to calculate cosine, sine, or tangent where it's a difference of two angles or a sum of two angles. The reason why these might be useful is that this formula, these ones, will allow us to find exact values for our trig functions for multiples of 15 degrees. Because, for example, if you wanted to find cosine of 15 degrees, you could think about how 15 degrees is the same thing as 45 degrees minus 30 degrees. And then you could just apply your difference identity. And that means that finding cosine of 15 really is going to be in terms of finding cosine and sine of 45s and 30s. Or similarly, if you wanted to find cosine of 75 degrees, 75 is the same thing as 30 plus 45. So again, finding cosine of one of these angles, 75 degrees, could be thought of in terms of a sum of two angles, in which case we would just need to find sines and cosines of 30s and 45s. So let's start with this first problem, finding cosine of pi over 12. Pi over 12 radians, that's the same thing as 15 degrees. And we know that 15 degrees is 45 degrees minus 30 degrees. So when we're thinking about pi over 12 radians, that's the same thing as pi over 4 minus pi over 6. So that means that when I'm looking for cosine of pi over 12, I'll instead be thinking of it as cosine of pi over 4 minus pi over 6. And now I can just use that identity, the cosine difference identity. That cosine of one angle minus another is cosine of the first angle times cosine of the second plus sine of the first angle times sine of the second. And at this point, you just need to use your special triangles to find out what is cosine of 45 degrees, root 2 over 2, cosine of 30 degrees, root 3 over 2, and then the same thing for sine, root 2 over 2 and a half. So just using my special triangles now to evaluate those exact values of sines and cosines, and then simplifying. We have root 6 over 4 plus root 2 over 4, which is root 6 plus root 2 all over 4. So using my difference identity for cosine, I was able to find cosine of pi over 12, cosine of 15 degrees. And I can do the same thing for cosine of 7 pi over 12. 7 pi over 12, if we were to, on the side, figure out what that is in terms of radians, 7 pi over 12 radians is the same thing as 105 degrees. And if you're thinking about 105 degrees, you know that that could be thought of as 60 degrees plus 45 degrees. So you could say, well, then that 7 pi over 12 radians is pi over 3 plus pi over 4. So that means when I'm looking for cosine of 7 pi over 12, I'll be thinking of it as cosine of pi over 3 plus pi over 4. And now we just need to use our sum identity for cosine. Cosine of one angle plus another is cosine of the first angle times cosine of the second minus sine of the first angle times sine of the second. And then you would just use your special triangles to find out what is cosine of pi over 3. It turns out to be 1/2. Pi over 4, cosine of that, root 2 over 2. Sine of pi over 3, that's root 3 over 2. Sine of pi over 2, pi over 4, that's root 2 over 2. And then simplifying, we have root 2 over 4 minus root 6 over 4, which is root 2 minus root 6 all over 4. Now, one of the nice properties of these identities is that even though there are 6 identities in total, you can actually generate all of the identities from only one of them. And so by that I mean, if we know the identity for cosine of alpha plus beta, or alpha minus beta, we can generate the other cosine identity, and then from that generate the sine identities from alpha minus beta and alpha plus beta, and then from that generate the tangent identities for alpha minus beta and alpha plus beta. So that's what we're going to do for the rest of this part of the video here. We're going to be generating the other identities. So here we're going to use the difference identity that we know. We know that cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. And what we'd like to do is use that to generate the identity for cosine of alpha plus beta. And so the idea that I'm going to use here is that if you're thinking about cosine of alpha plus beta, that's the same thing as cosine of alpha minus negative beta. And by rewriting things this way, I've now expressed it in a way where I can use my difference identity. This is now cosine of one angle minus another angle, and we know how to find cosine of one angle minus another, so that's what I'll do. I'll use that difference identity, and it should be cosine of the first angle, cosine of the second angle, plus sine of the first angle, sine of the second angle. And now I'm just going to use what I know about the symmetry of my sine and cosine functions. I know that cosine is even, and so that means that cosine of negative beta is the same thing as cosine of beta. And sine is an odd function, so we know that sine of negative beta is negative sine of beta. And lo and behold, there we go. We have our identity that cos of alpha plus beta is cos alpha cos beta minus sine alpha sine beta. So using our identity for cos alpha minus beta, we've now generated our identity for cos alpha plus beta. Now we're going to take a look at these two identities for sine. And the two identities we have, a difference identity and a sum identity, and both of these we'll be able to generate only knowing the cosine identities. And this is really just using our old friend, the complementary angle theorem. Remember that the complementary angle theorem said if you have two functions that are cofunctions of each other, and if the angles are complementary, then the two functions have to be equal to each other. So for example, if you're looking at sine of 30 degrees and cosine of 60 degrees, you know that because sine and cosine are cofunctions, and because these angles add up to 90, that therefore these two things must be equal. Or similarly, if you were looking at cosine of, let's say, 10 degrees and sine of 80 degrees, these two are cofunctions, and the angles add up to 90, so therefore these two things must be equal to each other. So more generally, we could just say that for any angle theta, you know that sine of theta and cosine of 90 minus theta, or pi over 2 minus theta, that those would have to be equal, and that's because sine and cosine are cofunctions, and these angles, theta and 90 minus theta, they add up to 90. Similarly, you could also say that cosine of theta and sine of 90 minus theta, that those are also equal to each other, again because you've got cofunctions where the angles add up to 90. So to generate the sum identity for sine, that's what we're going to use. We're going to use the fact that for sine of an angle, that's the same thing as cosine of 90 minus that angle. That's, again, the complementary angle theorem just being used here, that we could express sine in terms of cosine if we wanted to. And if we're looking at cosine of pi over 2 minus alpha plus beta, I could really rewrite that as cosine of pi over 2 minus alpha minus beta, just carrying that minus through the bracket. And so that means that I could really think of this as cosine of pi over 2 minus alpha minus beta. So I really have now a difference of two angles. The first angle is pi over 2 minus alpha, the other one is beta, and I'm looking at cosine of this difference of angles, and I know exactly what to do. We have two formulas, one for cosine of an angle plus another, and one for cosine of an angle minus the other. And I have cosine of one angle minus another, and so I'm going to use that formula, which is that it's cosine of the first angle, cosine of the second angle, plus sine of the first angle, sine of the second angle. And much in the same way that we used the sine function and expressed it in terms of cosine via the complementary angle theorem, we're going to do the same sort of thing here. If you're looking at what we've got here, we've got cosine of 90 minus an angle, and by the complementary angle theorem, we know that that should be sine of our angle. So cosine of pi over 2 minus alpha is the same thing as sine of alpha by the complementary angle theorem. And same thing with the next term, we've got sine of 90 minus alpha. That's the same thing as cosine of alpha, again using the complementary angle theorem. And if you were to go back a page, you could see that yes, we have indeed shown that sine of alpha plus beta is equal to this. This is our identity, the sum identity for the sine function. And if you're thinking back to what we did a couple slides ago, where I used one cosine identity to generate the other, we're now going to do the same thing here, because now that we've generated the identity for sine alpha plus beta, we can go ahead and use that to generate the formula for sine of alpha minus beta. And that's because sine of alpha minus beta could be expressed as the sum of two angles if you thought of it as sine of alpha plus negative beta. And so we know our formula for one angle plus another. We just figured that out on the previous page, that sine of alpha plus beta would be sine of the first angle cosine of the second plus cosine of the first angle sine of the second. So using that here, we've got the first angle is alpha and the second angle is negative beta. So that's sine alpha cosine negative beta plus cosine alpha sine negative beta. And then, just like before, we're going to use the even and odd properties of our trig functions. Cosine is even, so cosine of negative beta is equal to cosine of beta. Sine is odd, so sine of negative beta is negative sine beta. And there we go. We've now generated our identity for sine of alpha minus beta. I'm not going to do both of these identities. They're really kind of the same here as far as how I would generate them. I'm going to do the very first one, tangent of alpha minus beta. And I'm going to use one of the things that we said at the very beginning of trigonometry, which was that if you're thinking about tangent, it could be expressed as sine divided by cosine. So if we have tangent of alpha minus beta, that's sine of alpha minus beta over cosine of alpha minus beta. And we know those. We have both of those identities already figured out, so let's go ahead and use them. Sine of alpha minus beta, that's sine alpha cos beta, minus cos alpha sine beta. And then we've got in the denominator cosine of alpha minus beta. That's cos alpha cos beta plus sine alpha sine beta. Okay, so what I'm going to do next, because if you're taking a look at these identities, you can see that they're not left in terms of sines and cosines, they're left in terms of tangents. So I have something here right now which is a bunch of sines and cosines of alphas and betas. And to make those tangents appear, what I'm going to do is take each of the terms in the numerator and the denominator, and I'm going to divide them all, top and bottom, by cosine alpha, cosine beta. And one of the things that we'll see here is that when I'm doing this, there's going to be quite a bit of cancellation. So there's a lot of cosine alphas and cosine betas that will cancel out, and then what I'll be left with will be some tangents after a little bit of thinking. So let's just write this down. And then we'll do our canceling. So we can see in the numerator that there's a cos beta over cos beta that cancels, and a cos alpha over cos alpha that cancels, another cos alpha over cos alpha, and a cos beta over cos beta. So what do we have? Well, we're left with, in the numerator, you've got sine alpha over cos alpha, which is the same thing as tangent of alpha, minus, you've got sine beta over cosine beta, which is tangent beta. And in the denominator, we have 1 plus sine alpha over cos alpha, that's tangent alpha. Sine beta over cos beta, that's tangent beta. I'm just going to write that a little bit nicer. So we have in the denominator 1 plus tangent alpha times tangent beta. And there we go. You can compare this with the formula that we have above, and you can see that, yes, indeed, we've shown that tangent of alpha minus beta is tangent alpha minus tangent beta over 1 plus tan alpha tan beta. Now, as far as the other identity goes, if we wanted to show this one instead, the steps are pretty much the same. We'd be looking at tangent of alpha plus beta, which would mean we would have sine of alpha plus beta over cosine of alpha plus beta. And all that's really going to do is change the signs. Sine of alpha plus beta, that sign would be a plus. Cosine of alpha plus beta, that sign would be a minus. So you can see that without too much work, you would get exactly the identity that we have for the sum identity for the tangent function, basically doing the same steps, just this time with sine of alpha plus beta and cosine of alpha plus beta.